in this example, we are required to find the stationary point of inflection for the graph with this equation. So the first step will be to find the first and the second derivative. So step 1, find the first and the second derivative. So the first derivative is 3x squared plus 12x plus 12, and the second derivative here will be 6x plus 12. Okay, now the second step is to set the second derivative equal to 0 and solve for the potential inflection point, because we know that inflection points occur where the second derivative is equal to 0. So step 2, set the second derivative equal to 0 and solve for the potential inflection point. Now, our second derivative is 6x plus 12. Equate that to 0, which means 6x will be equal to negative 12, which means that x will be equal to negative 2. So we suspect that there should be a point of inflection at x is equals to negative 2. So step 3 will be using a sign diagram, okay, for the second derivative to check for change in concavity around the potential inflection point. So use sign diagram. So we suspect that there should be inflection point at x equals negative 2, but how do we know? We need to check for change in concavity. So which means we are going to basically draw a sign diagram, and here we'll have, these are x values, and we suspect that there is an inflection point at x equals to negative 2, and what we want to do is to investigate the signs of the second derivative. So I'll pick the point to the left. So these are points that will help me to know, and they're just test points to help me to figure out if the signs of the second derivative are changing. And if they're changing, they will be changing concavity. So plug in, for example, negative 3, and here plug in a number like 1. So you plug those into the second derivative, okay? Now, if you plug in negative 3, you'll get negative 6. If you plug in 1, you'll get 18, which means here we have negative, here we have positive. So, which means that concavity changes at x is equals to negative 2, hence it's a point of inflection. So from here, we can see that concavity changes at x is equals to -2. Hence, it is an inflection point. Okay, so but the question is asking for a stationary point of inflection, which means we need to be able to do something else. We need to use the first derivative to determine if it's a stationary point of inflection. So that leads us to, because the question is asking for stationary point of inflection, we know that the first derivative should be equal to 0 and the second derivative is equals to 0. So we need to check the first case here, which means we have to go to step step 4. Now step 4 is use the first derivative to determine if it is a stationary point of inflection. Okay, so we are using the first derivative, okay, to check if it's a stationary point of inflection. So what do? You just plug in -2 in the first derivative, okay? So if you take the first derivative, plug in -2, okay? So you basically take the first derivative, this one here, you plug in -2, what do you get? You get 0. So we can say it is a stationary point of inflection. So hence, it is a stationary point of inflection. Okay, let's carry on. So is that the end? No, there's a final step. The final step is trying to find the y coordinate. So step 5, find the y coordinate. So basically you plug in 2 into the original function. Okay, you plug in -2 into the original function, this function here. So if you plug in -2 in the original function, it will be -3. So we can say that there's a stationary point of inflection at -2, -3. So there is a stationary point of inflection at -2, -3.